Let's look at a more complex molecule, cocaine. We start with this aldehyde and use lithium diisopropyl amide and tributyl stanyl hydride. This first forms a tin lithium reagent, and that essentially behaves as tin minus, attacking at the aldehyde and giving us this species here as our first product. A quick workup removes that lithium and replaces it with a proton. The next step is the reaction of phthalimide via the Mitsunobu route, which is a good way of replacing an alcohol with a generic protonated nucleophile. Once we've got that product, we deprotect the phthalimide using hydrazine to give us an amine as the product. We'll go through the mechanism of the phthalimide deprotection. First, the hydrazine attacks one of those carbon-oxygen double bonds, then our NR group is the leaving group. The second step happens intramolecularly and liberates our amine and generates this 10-pi aromatic stable byproduct. Once we've got the terminal amine, we react it more of the starting material. We get a condensation reaction between those two groups. It's pretty simple, and we get this imine product with the loss of a molecule of water. Once we've done that, we use N-butyl lithium to perform a metal exchange and swap that tin atom for a lithium atom. That product essentially behaves as if it had an anion in that position. And that's important for the next step of the reaction scheme, which is a cycloaddition with this substituted ethene here. The electrons flow around the circle and generate this 5-membered ring as our product. It's a 4+2 cycloaddition, and it's worth going into that in a bit of extra detail to discuss the Woodward-Hoffmann rules. So I'll draw the reacting species out here along with the p orbitals that comprise their pi systems. That anion is conjugated with a nitrogen-carbon double bond, and the lobes of the systems interact on the same face, that is, their suprafacial components. We have a pi4 suprafacial component and a pi2 suprafacial component. That means the total number of 4q plus 2s components is odd, and it's allowed by the Woodward-Hoffmann rules. We now have this product. The nitrogen has become protonated during the workup, and we need to do some extra steps on it. We want to reduce away this sulfur, and we'll use metallic lithium in liquid ammonia to do that. We want to protect the nitrogen using Bock anhydride, and we want to deprotect and oxidize these groups here and convert them to aldehydes. All of these mechanisms are a bit boring, so I'll just skip to the product of these 3 steps, which is this. I'll also draw in the relative stereochemistry because the cycloaddition was a syn-specific reaction. The next step uses L-proline as a chiral catalyst. This ensures we only get one enantiomer of our product, which is important because cocaine is optically active. There's an intramolecular condensation between an enol and one of the aldehydes, and I'll draw numbers on the carbons so you can see where the ring forms. The product of the cyclization reaction is this, and you can trace the ring around. It's probably profitable to redraw this in the more traditional cyclohexane-like plan. And we can again trace the path where the new ring has been formed by the intramolecular reaction. That's formed the main skeleton, and there are a few more transformations left. We want to oxidize the aldehyde using sodium chlorate and methylate it using diazomethane. This provides a highly reactive methyl group by SN2, which will turn pretty much any oxygen into an O-methyl group with the loss of nitrogen as an excellent leaving group. Once we've done that, we want to work on the alcohol. We'll add our benzyl group next using this anhydride. And then, finally, we want to deprotect the nitrogen and methylate it. For our deprotection, we'll remove the Bock group using trifluoroacetic acid, and the methylation we'll use formaldehyde and then reduce it with sodium cyanoborohydride. That completes the synthesis of cocaine.